Chapter 13 is on kinetics. Kinetics is defined as the study of the speed or rate of a chemical reaction. People who study kinetics study things like how fast a reaction takes place. So if you want to be able to predict when the reaction is complete or how much longer it needs to cook before it's done. They also study what kind of conditions dictate the speed of the reaction, and they learn how to control the rate of the reaction. So if you want to make a reaction go faster, or if you want to make a reaction go slower, how can you alter the conditions to get it at the speed that you want? In the first section, we're going to mostly be talking about the rate of reaction. And the rate of a chemical reaction is defined as change per time, like any rate. And in chemistry, we're looking at a change in concentration per time. Typically, the concentration is measured in terms of molarity. So the units of rate conventionally are molarity per second. And time is usually measured in seconds because reactions are usually pretty quick. And the change in concentration in this equation can be defined in terms of any product or any reactant. You get to choose whether you want to define the rate in terms of a product or a reactant and which one. And usually we're going to choose the one that is easiest to measure. So, for example, consider the production of ammonia from nitrogen gas and hydrogen gas. If we wanted to monitor or measure the rate of this reaction, we could choose to calculate it using any one of the three chemicals that are in this equation. So we could calculate the rate in terms of the consumption of the nitrogen gas, if we decided that the nitrogen gas was the easiest molecule to monitor in this reaction, then we could just watch how quickly the concentration of nitrogen drops over a course of time. Or it could be the consumption of hydrogen gas. If that's what we chose to monitor. Or it could be the production of the ammonia gas. We could choose any one of those three to determine the rate of this reaction. So, because this reaction's got two different products in it, it's kind of a tricky one to start with in terms of doing the math. So for our first real example, we're going to consider a really simple reaction. It's totally generic, not even real molecules. Molecule A turning into molecule B. So this one's really easy to consider because it's just one reactant in one product. Some examples of reactions that fit this A goes to B format would be something like the conversion of O2 to ozone, or the dissociation of Cl2. Those are just examples of A goes to B types of reactions. If we wanted to measure the rate of this reaction, we would either choose to monitor the consumption of A or the production of B, whichever is easiest to measure. And the rate of this reaction, if we were monitoring the consumption of A in order to determine the rate, then the rate of this reaction would be written as, because A is being consumed and its concentration is being decreased, it would be a negative change in concentration. And we would write that using this notation. Looks like this: delta for change. The square brackets represent molarity per change in time. So this A in the brackets means molarity of A. We'll use this bracket notation quite a bit, especially next quarter, and it just represents molarity. It just means the molarity of whatever is inside of the brackets. If we chose to monitor the production of B in order to determine the rate, then the rate, because B is being produced, the concentration is increasing. So this would be a positive change in concentration of B per time. And if we were to actually do this, maybe in terms of both, and graph out the way the concentrations change per time, let's see, molarity versus time, we would find that, let's see, if we're thinking in terms of A, because A is the reactant, we're going to start with a pretty high concentration of A. And B, being the product, we're going to start with no B at all present, 0. And as time progresses, B is produced, so its concentration goes up until it hits a maximum amount, and then it just plateaus. And at the same time, the concentration of A is going to drop until it hits a minimum, and then it plateaus. That's for an A goes to B reaction. Notice that the concentration of A never drops down to 0 in this graph that I have, the way that I've drawn it. This reaction, we'll say, does not go to completion because the A doesn't get completely consumed. And that's not unusual.